For today's review video, we're going to be talking about the topic 10.1, Taylor polynomials. Before we get started with Taylor polynomials, we're going to go over a few things that we need to know before we solve Taylor polynomials, and one of them are high order derivatives. So here we can see that to find the derivative of an f of x function, we have this little apostrophe little thing above the f, and that shows that it's the derivative. So for instance, if we have f of x equals 2x, then the derivative of that would be 2. We symbolize derivatives with this little apostrophe. Now, higher order derivatives mean we're solving for the derivative of a derivative, and so on. So this right here is the first derivative. We are going to be needing to find the second derivative, which can be represented with two apostrophes or just the number, as well as the third derivatives, and so on. So, for example, if we are trying to find the third derivative for f of x equals 2x to the fourth, the first derivative would just be using our power rule. 4 times 2 is 8. X to the third. Our second derivative would be 24x squared. And then our third would be 48x. So essentially, you are just taking the derivative of a derivative. And then if we were to find the fourth derivative, it would just be 48. Mm. And now the most important thing to look for while we are solving for these is to look for patterns. So, for example, for this problem, I can see that the coefficient and the exponent are getting multiplied, and then we are subtracting 1 from the exponent. So we can write that as n to the x n minus 1. So our exponent here comes out, it's getting multiplied with the coefficient in front, and then 1 is subtracted from the exponent. So we're going to need to know how to find higher order derivatives as well as look for those patterns. Another important thing that we need to know are factorials. Factorials are symbolized by this exclamation mark symbol, and essentially it's just numbers being multiplied together in order. That's a little confusing, but for example, if I had the fifth factorial, that would just be 5 times 4 times 3 times 2 times 1. So it's all the numbers from 5 going down being multiplied together. Okay, now that we know some of the basics, let's look at the formula and then solve the problem. So Taylor polynomials we can solve by these two formulas right here. These are for solving Taylor polynomials if a equals 0. So we have a of 0 plus a of 1 plus a of 2 and so on, plus a of n x to the n, and this right here is why it is so important that we need to be able to look for patterns. Okay, let's get into a problem. Okay, so find the Taylor polynomial at 0 where f of x equals e to the negative x over 6, semicolon, p of 3 equals x. This p3 of x, means we are looking for the third derivative. So here I have my starting, which is e to the negative 1 over 6x. I separate the x from the fraction just to make it a little bit easier for me. Now using our power rule, the negative 1/6 gets brought out, and again, negative 1/6 getting brought out, and we do that until we have our f of 3, our third derivative. So that is step number 1, finding your derivatives. And now our step 2 is to find coefficients. Oh wait, sorry, not finding coefficients. We are plugging in 0 to get our, we're plugging in 0 because our polynomial is at 0. So for each of my derivatives I have found, we're going to be plugging in 0 in for x. And when I do so for my f of x through f3, 0, I get these values over here. 1, 1, 1/6, 1 over 36, and 1 over, and then negative 1 over 216. Okay, now our third step, we are going to be looking at this second formula right here. For our third step, that is where we are going to be finding our coefficients for our polynomial equation, which up here is f of 0 plus f prime of 0 x plus f2 of 0 over 2 factorial x squared, and so on. So for this equation, those values are from this equation up here. So our f of 0 is just a of 0, f prime of 0 is just our a1, but then for a2, we need to do a bit of math here, which is f2 0 over 2 factorial. And then if we were to get our a3, that would be f3 0 over 3 factorial, and so on. So I have the formula written here, and then once I plugged in my values and got a of 2 and a of 3, this is what I got. Or wait, I'm plugging, sorry, these are my values from up here. Once I plug them in, these are the values that I get. So our a of 0 is just f of 0, our a1, negative 1/6, but then we need to do 1 over 36 over 2 factorial, and that's what I got. I, n- this I got 1 over 72, which is in my final equation. And that would be our answer. So that is how we find a Taylor polynomial when that's how we find a Taylor polynomial at 0. Now, another scenario is finding Taylor polynomials when it is not at 0. So I'm just going to use this problem and go over it kind of briefly. But in that case, we would need to find an a value to plug into our f of x. So for instance, if we had f of x equals square root of x, we would want to pick a value to go in here. And it's very important when choosing that value because we want it to be easy for us. So if I have the square root, I would want to pick a value that can be square rooted, such as 4, 9, 16, and so on. The square root of 4 is 2, square root of 9 is 3, square root of 16 is 4. Those are easy. So we would do the same steps as if it were at 0, but then we would find a value, plug it in for our x's, and approximate it. So that is what we would do to find Taylor polynomials at 0 and when it is not at 0.